Hey everybody, I hope you're all doing well. Today is going to now be lesson 3 in our logarithmic and exponential functions unit. Now, today's primary focus is on solving exponential equations, so solving an equation where there's a variable inside the exponent. There's a couple of different ways we can do that, and today is only focusing on one of them. I think it's the easier one. And it works really well when it works, but what you're going to find is it's not always going to work, just depending on the setup that you have, okay? And then when we get to a question where we realize it doesn't work, we'll kind of pause that conversation and we'll pick it up in a next lesson or in a soon-to-be lesson on other tools that we can use to solve. So today is going to be all about shifting or rearranging the equation so that the bases are the same, okay? Now, before we get into that, let's just kind of review how I might want to do that graphically first. So this first question here is graphically solve the following. 2 to the x equals 8 to the x minus 1. Now, if we're going to graphically solve this, y1 comes from the left side, y2 comes from the right side. One thing just to be careful of when you do that, if you are a white Casio or you're an older model TI, you got to make sure with that 8 exponent x minus 1, you have to input that as 8 and then push your exponent button and then open up a bracket. The x minus 1 is going to have to be in a full set of brackets so that your calculator knows that whole thing is the exponent. If you're a newer Casio or a newer TI, you won't have to do that because when you open up or when you press the exponent button, that little box opens up. And as long as you're in the box, that's okay. I would pause me, get a picture so that you can compare. This is the picture that you should have gotten. Notice that my window settings are going from -6 to 6 on the X and -2 to 6 on the Y. And when you do the intersection of that, if you're a Casio, you're going F5, F5. If you are a TI, you're going second trace 5, enter, enter, enter. And you get an x value of 1.5. A reminder, we don't care about the y value here because there was no y in this equation, okay? We were just solving for x, so the solution is the x value at the point of intersection, okay? The next one to try is 4 to the x plus 5 equals 1 over 16 to the x. Again, I'd like you to pause me and graph this yourself, and then we can compare. So the picture that you should have seen is something like this. And when you do the intersection, you ended up with x equals -1.7. Okay, so now we're going to turn our attention to doing this algebraically. And to do it algebraically, we're going to start with the exact same first two examples that I just showed you, but we're going to do it from an algebraic standpoint. Okay, so in order to solve this algebraically, what I want to try and do is I want to try and make my bases the same. So I'm taking a look at this 8, and I'm asking myself, okay, is there a way to write 8 as 2 to the something? Can I write it as a power with a base of 2? Just like the power with a base of 2 that I see on the left side of the equation. And the answer to that is, of course, yes, 8 is 2 to the 3. So what I'm going to do is I'm going to replace my 8 with 2 to the 3. Okay, everything else stayed the same, but where I saw 8, I replaced it with 2 to the 3. Now, what I see here is an exponent to an exponent, or power of a power, sometimes you hear that called. When I have an exponent that's to another exponent, I end up multiplying those exponents together, if you think back to your grade 10 exponent laws. So that's going to become 2 to the 3x minus 3. Now, I have 2 to the x equals 2 to the 3x minus 3. What I've been able to do here is I've been able to rearrange or rewrite this equation so that I have the same base, a single power with the same base on either side of the equation. The next statement may sound very simple to you, but it's very profound for what we have to, or what we get to accomplish with it. If 2 to the something equals 2 to the something, then my somethings have to be the same thing, which means when I have this set up the way I do, those exponents have to actually come out to be the same number. And that allows me to now solve for x. I just pull the exponents out and say, okay, this now means that x has to equal 3x minus 3. And I solve from there. I add 3 to both sides. I subtract x from both sides, and then I'll divide by 2. And so I end up with a statement that reads x equals 3 over 2. Now, don't lose what we just did. We found the value for x that if I was to plug it back in here, if I was to put 3 over 2 here and 3 over 2 here, I would get a true statement. That is the one value for x that makes this equation true, okay? And that's what we're always trying to figure out when we're trying to solve an equation. Okay, so the second one, oh, let me take that ink off for you. The second one, just like the second one we did with graphing, we're looking at 4 to the x plus 5 equals 1 over 16 to the x. So I'm going to take a look at this 1 over 16, and I'm going to say, okay, can I make that be 4 to the something? Again, I have to take you back to grade 10. We have to think about exponent laws. You know that 4 squared equals 16. Well, if 4 squared equals 16, and I need to flip that to get 1 over 16, then I'm going to write that as 4 to the negative 2. 4 to the negative 2 and 1 over 16 are the same thing. So I replace my 1 over 16 with 4 to the negative 2. Okay? It is super important at this stage of the game, when you've written them like this, look and compare that to where you were. Does 4 to the x plus 5 still equal 4 to the x plus 5? Does 4 to the negative 2 to the x still equal 1 over 16 to the x? Okay, you don't want to change any of the values here. Okay, so we're good. So now we're just going to work on continuing to solve this portion here. So this becomes 4 to the negative 2x. And now that I've written them as a single power with the same base, I know the exponents have to equal each other, so I can say x plus 5 has to equal negative 2x. I'll subtract x from both sides, and then I can divide by the 3, and that gives me negative 5 over 3. Okay, just for clarification, I said subtract x from both sides there. Really, I added the 2x to both sides and subtracted the 5. Okay, it doesn't really matter which way you do it, you're still going to end up with x equals negative 5 over 3. Okay, good. Next example, this one's actually probably easier because they're already set up as a single power with the same base. So I just pull the exponents out. 2x plus 3 equals 7. Subtract the 3, divide by 2, and I get x equals 2. 7 to the x minus 2 equals 343. Well, again, I'm going to ask myself, can I take this 343 and can I write it as 7 to the something? And for that, you end up playing in your calculator a little bit until you figure out whether it works. It doesn't take you long to find it if it exists or to know it doesn't exist. In this one, it does exist. I can rearrange that so that 343 can be written as 7 to the 3. So I've got 7 to the x minus 2 equals 7 to the 3. I've now written it as a single power with the same base, so I know my exponents have to equal each other. X minus 2 equals 3 and x equals 5. Okay, now we're getting a little fun. 3 to the x equals 27 root 3. Again, I want you to see that it's 3 to the x on the left side, so kind of the game I want to play here is, can I make 27 be 3 to the something? The answer to that is yes. 27 is 3 cubed. Can I make the root of 3 be 3 to the something? Again, I have to take you back to grade 10 and we have to review some exponent laws. The root 3 can be written as 3 to the 1/2. So what I'm going to do is I'm going to write everything as base 3 first. So I've got 3 to the x equals 3 to the 3 times 3 to the 1/2. Just like I said in a couple slides ago, make sure at this stage, go back to where you were. Does everything equal? Does 3 to the x equal 3 to the x? Yes. Does 3 to the 3 equal 27? Yes. Does 3 to the 1/2 equal root 3? Yes. Now, be careful with this guy. I do not have these written as a single power yet. I need to now do this multiplication. When I'm multiplying powers with the same base, I add the exponents. So 3 plus 1/2 is 3.5, or 7 over 2. And now I have them written as powers with the same base. single power with the same base, so I can pull the exponents out, and x equals 7/2. Okay, now 27 to the x minus 2 equals 1/81 to the x plus 3. I would love it if you paused me right now and tried this yourself. So all of this can be written with base 3. That's the first thing I'm going to do. I'm going to change this 27 to be 3 to the 3. 81 is 3 to the 4, so I can change this to be 3 to the negative 4. Okay, now I want to make sure I distribute my exponent here and distribute the exponent here, because I'm taking a power of a power. I have to multiply the exponents together. So that's 3 to the 3x minus 6 and 3 to the negative 4x minus 12. Now I've written it as single powers with a common base. So I know the exponents have to equal each other. 3x minus 6 has to equal negative 4x minus 12. And then I go ahead and solve it. Add 4x to both sides, add 6 to both sides. I get 7x equals negative 6. So x equals negative 6/7. A gentle reminder, you would always want to answer these in exact value unless you are explicitly told some sort of rounding instructions. If you are not told any rounding instructions, this should always be answered to exact value answers. Okay, 49 times 7/12 to the 2x equals 144. Couple of things I need you to think about here. First of all, a very common mistake that kids do is they take that 49 and multiply it by the 7/12. You can't do that because of the 2x. That exponent only applies to the 7/12. So instead, you have to look at this and say, I have to get rid of the 49. How am I going to get rid of the 49? I'll divide both sides by 49. Okay? Now I'm thinking to myself, okay, I want this to say 7/12 on both sides, or I want it to say 12/7 on both sides. It doesn't really matter as long as you make them say the same thing. Okay, I'm actually going to leave the 7/12 on the left, and I'm going to pick on this guy. I know that 49 is 7 squared, and I know that 144 is 12 squared. So that would actually give me 12/7 to the 2. Now, that's not what I want. I want 7/12. So I'm also going to flip that. So I'm going to call that 7/12 to the negative 2. Okay. Now, I know I've said this a couple of times, but here's where it becomes really important. At this stage, you want to make sure you did it right. You want to make sure you have not changed anything from above. So you're going to ask yourself, does 7/12 to the 2x equal 7/12 to the 2x? Yes, those say the same thing. 7/12 to the negative 2. Does that equal 144/49? If I stuck 7/12 to the negative 2 into my calculator, would it give me 144/49? And the answer to that is yes, it does. Now, I've written this as a single power with the same base. So I know the exponents have to equal each other. So now I can say 2x equals negative 2 and x is negative 1. Okay, what do you think I want you to see here? I want you to see a quadratic. Okay, so the easiest way to handle this probably is with substitution. So let 4 to the x equal a. Okay, if I did that, 4 to the x equals a, this is going to leave me with a squared. This is going to leave me with negative 6a, and this is going to leave me with 8. So now I factor that. I'm looking for two numbers that multiply together to give me 8 and add together to give me negative 6. So that factors into a minus 4 and a minus 2. That means a would be 4 and a would be 2. But remember, this question had nothing to do with a. A was a substitute for 4 to the x. So now I have to substitute it back and actually solve for what x is. So 4 to the x equals 2. Well, if 4 to the x equals 2, x would have to be 1/2 because the square root of 4 is 2. And then my other statement would be 4 to the x equals 4. Well, if that was true, x would have to be 1. So I have two answers for this guy, two things that actually work in this equation. If I was to plug 1/2 in for x here and here, this statement would be true. And if I was to plug in 1 for x here and here, this statement would be true. There are two possibilities for x. Okay? All right, this was a released diploma item from a while back. A student is asked to solve the equation 125 125 to the x times x plus 1 all over 5 to the 3x minus 4 equals 25 to the x minus 5 using an algebraic process. Now, she's able to simplify the equation to the form 3x squared plus bx plus c equals 0. What is c? Okay, so probably in order to try and work with this, we want to get it as the same base. I'm looking at 125 as a base, I'm looking at 5 as a base, and I'm looking at 25 as a base. So the very first thing I'm going to do is write that all as base 5. 125 is 5 to the 3, then 5 is 5, and 25 is 5 squared. So I'm looking at this right now. I've changed my 125 to 5 to the 3, so I've got 5 to the 3x times x plus 1. I've got 5 to the 3x minus 4 on the bottom, and I've got 5 squared to the x minus 5. Now, these guys will get distributed, 3 to the x times x and 3 to the x times 1, 2 times x and 2 times negative 5. The other thing I have to look at is here, I'm dividing powers of the same base. If I'm dividing powers of the same base, I subtract the exponents. So ultimately, I'm going to have this guy subtract this guy. And when you do that, make sure that guy goes in a set of brackets because that subtraction sign will get distributed to both items in here, okay? So you want to be really, really careful of that. So I've distributed it here, 3x squared plus 3x, and then I'm saying subtract, and I put the 3x minus 4 in brackets, and then I've got the distribution of the 2 here for 2x minus 10. I'm going to clean this up a bit. This will be negative 3x and plus 4. And then I'll combine like terms. My 3x's are gone here. Bring my 2x over, bring my neg 10 over, and I get this quadratic. In the form A, B, C, we were asked for C. And I know I've got it right now because my A value is 3 here, and I notice up here my A value is also 3. So my C value is 14, and that's the answer. On your diploma a couple years ago, this was a multiple choice question. And the one reason I want to warn you of that is because if you had not distributed that negative here, if you had called this negative 3x and then this plus 4, that was actually one of the distractors. So you have to be really, really careful about that. Okay, solve the following algebraically. We would want to make the bases the same because that's what we've been doing all lesson. And I want this to puzzle you for a moment. And I want you to realize that you can't make the bases the same. Okay, so this strategy that we've been dealing with today, we can't actually do anything with for this equation. Okay, so we can't make these the same bases. We need another way to do this. There is another way to do this, but that conversation will be continued in another lesson or two. Okay, all right, solve the following system. This is the last question that we'll do together. We want to make the bases the same first so that we can pull the exponents out. So I'm going to make the 9b3 squared. And then that gives me a statement when I pull those exponents out, x minus y has to equal 2. Over here, I'm going to make my 27b3 cubed. Now I have the same base, single power. I can pull the exponents out. I've got 3y equals x plus 2. So now I'm looking to solve this system, okay? Remember, a system is a series of two equations with two unknowns, which is what I've got here. I can solve by substitution or I could solve by elimination, whichever one you see fit. Whichever one makes the most sense to you, it doesn't matter. Both are algebraic processes. So I chose to rearrange my equation, and I'm going to do this by elimination. So what I've done is I've kept my x minus y equals 2, just as it was. But when I brought this guy down over here, I just brought my x over to the other side so that I could line everything up. Remember, when you solve by elimination, your x's has to be on top of your x's, your y on top of y, number on top of number, and your equal sign in the same place as well. Now, I can actually get rid of my x's. I can eliminate my x's by adding here because one's positive and one's negative. If I add that column, they're gone. Negative y plus 3 would give me 2y, and 2 plus 2 gives me 4. Divide by 2, and I know that y is 2. I take that information, plug it back into one of my original equations. So I took my x minus y equals 2, plugged in my y equals 2. That's where I got my x minus 2 equals 2, add 2 to both sides, and x equals 4. So the solution to the system, x is 4 and y is 2. Okay, your homework is posted here. And if you have any questions, feel free to connect. I think this is fun, so I hope you guys will have some fun with it. Take care, guys.